Hello, my name is Fernando Febres Cordero. I've been a grad student here at Florida State University in the Department of Physics, working with the High Energy Theory and Phenomenology group with Professor Laura Reina. I've been talking to you about my work on calculating quantum corrections to collider processes. The standard model of particle physics is one of the most successful theories that have been produced by the physics community. The standard model is a quantum field theory based on the gauge group SU3 for the strong interactions and SU2 cross U1 for the electroweak interactions. The particle containment of the model is given by three families of quarks and leptons and the force carriers, which are the gauge bosons. We know from experiments that the weak bosons W and C are massive particles, as well as quarks and leptons. To account for this is introduced into the model the so-called Higgs sector, in which a complex scalar doublet is added to the theory, and with a potential that has the shape of a Mexican hat, and has the property to produce a non-zero vacuum expectation value for the field, which by the end produces mass terms for the weak vector bosons, and even more, it can be accommodated mass terms for the rest of the fermion fields. A physical particle called the Higgs boson is left over. The current and future high-energy hadron colliders have as main goal to produce, to find out whether there exists or not a Higgs boson. Right now, the Tevatron at Fermilab is colliding protons and antiprotons at an energy of 2 TeV, and soon the LHC in Geneva will start running and will be colliding protons and protons at an energy of 14 TeV, and they will be able to assess completely what is the mechanism of electroweak symmetry breaking. Even more, the LHC will be able to explore the TeV scale completely, and maybe we'll find out that if there is or no new physics in that regime. In order to assess theoretically and compare to experiment at colliders, we use a key property of quantum chromodynamics, which is the fact that at high energies, the strong coupling constant becomes small. This allows to express observables in two pieces. One piece that is expressed in terms of the so-called partons, quarks and gluons, and that can be calculated perturbatively. And another piece that contains the information of the wave function of the hadrons that contains these partons. Even more, these different pieces can be expanded into series expansion in alpha S, where alpha S is the strong coupling constant. In quantum field theory, this series is organized through a diagrammatic representation called the Feynman diagrams. A Feynman diagram is a pictorial representation of a particle processes in which the lines represent the particle fields and the vertices are the interactions. At leading order, most of the processes are represented by the so-called tree diagrams. Diagrams that do not have any closed loop. And corrections are given by diagrams with more and more loops. Next to leading order, for example, corrections are given by diagrams with one loop. Once one has calculated these diagrams, one can extract information for observable. For example, in this slide, I'm showing some recent results we have got for CVB bar production at the Tevatron, in which you can see distributions for differential cross sections in terms of invariant mass of the BB bar pair. So finally, it is necessary to assess the phenomenological potential of the hadron collider, to study in detail and to have under theoretical control the signals. And for that, you need to go beyond the leading order. The complexity of these calculations grows exponentially with the number of loops and with the number of external particles that you are considering. So powerful techniques have to be developed to deal with them. And finally, I just said that the high energy physics community and the particle physics community is living very exciting times, because we're about to start exploring a whole new regime in the energy spectrum, the so-called TeV scale, where we might find new and unexpected physics. Thank you very much for your attention, and I hope you choose Florida State University for your grad studies.